Your learning journey starts now. Ever felt like these AI models are getting smarter, smarter, and maybe infinitely smart? What if they hit a wall we can't even see? That's the juicy mystery we're cracking open today. So, what kind of limit are we talking about? Think of it like this: there's the capability bound, the absolute best an LLM could theoretically achieve if you gave it infinite time, resources, and a very, very patient grad student. Then there's the cognizable bound. This is the real kicker. It's the limit of what we humans can actually test, verify, and understand about the model. Here's the plot twist. Often, the capability bound is way higher than the cognizable bound. Imagine a super powerful engine, but you can't build a steering wheel or brakes for it. Suddenly, that infinite potential feels less infinite, doesn't it? We might be building things that are incredibly powerful, but we're losing touch with what we can actually control or trust. This gap isn't just about the model anymore, it's about the whole system, model, human, and our institutions. Okay, let's get down to brass tacks. First up, physics. You can't compute forever without power, right? Every calculation needs energy, generates heat. There's a physical limit to how much computation you can squeeze out before things melt. Simple thermodynamics says no infinite chains of irreversible steps on a finite battery. Then there's the math gods throwing curveballs. The halting problem, still unsolvable. NP-hard problems, they get exponentially nasty fast. Gödel showed us some truths are provably unprovable within any strong enough system. So even in theory, there are mathematical boundaries. And guess what? In practice, LLMs often hit these computational ceilings way before their parameter count suggests they should. It's like expecting a car to go Mach 5 based on its horsepower alone, ignoring aerodynamics and material science. Now let's talk data and design. Models learn from finite datasets. No matter how big, it's still just a sample. The real world has long tails, rare events, stuff the model hasn't seen. This leads to out-of-distribution surprises and identifiability issues. Different causes can look the same. More data helps, but only up to a point. Then there's architecture. Longer context windows sound great, but attention gets diluted over vast sequences. Retrieval becomes noisy, and figuring out which early tokens caused later errors gets tricky. It's like trying to remember a conversation from 10 years ago, details blur, and optimization. Just because a network can theoretically represent something complex doesn't mean gradient descent can find it. Training can get stuck in local optima. Finally, semantics. Compression always loses information. Abstraction relies on assumptions, so the model's understanding isn't a perfect mirror, it has blind spots. So we've got physical limits, math limits, data limits, architecture limits. But here's the final boss, the verification horizon. Our ability to check these models has its own bandwidth and cost constraints. Think about verifying a proof longer than a human can realistically read or understand. Suddenly, we need automated proof checkers, formal systems, simulators. When the model's capabilities outstrip our direct verification capacity, we shift from relying on individual intuition to institutional audits using complex tools. This doesn't mean the model is truly infinite. It means our human-in-the-loop verification boundary has been pushed to its limit. The perceived infinity comes from our inability to keep pace with verification. So the real limit isn't just the models, but the entire coupled system's ability to maintain trust and verifiability. That's the frontier.